and I will talk about the field quantization. Field quantization has this Hamiltonian in previous case, and we derived the interacting Hamiltonian. Interacting Hamiltonian is that quantized, but field quantization is that Hamiltonian should be quantized. Actually, at first, first quantization is the energy quantization, and energy quantization means that the Hamiltonian should be quantized. And Hamiltonian basically from the classical mechanics, and we already know that the Lagrangian is the T minus V. It is the kinetic energy x dot square minus Vx. It is Lagrangian in this case, and the canonical momentum is that the P equal to partial L partial x dot is the canonical momentum mx dot from the classical mechanics. And so Hamiltonian, definition of Hamiltonian as a function of momentum as momentum and displacement, momentum and coordinate, and the canonical momentum is a px dot minus L. So it is that p square plus vx, that is that Hamiltonian in classical. So, and here in this case we think about that electromagnetic wave. So, and Lagrangian in electromagnetic field. Lagrangian is that as a function of velocity. Velocity means that here it is as a function of vector potential, time derivative of vector potential and real vector potential. Then it is energy current. Energy current is that E square plus B square, but in Lagrangian case, it is a volume integration as the E square minus B square. That is that case. Then here, electric field 1/8 pi and volume integration, and also electric field is that minus gradient phi minus 1/c partial A partial T, that is the electric field, and the magnetic field is here minus. Magnetic field is that it is square. Yeah, okay. That is curl A is the magnetic field. So it is a Lagrangian in electromagnetic field. So we already know that it is Coulomb gauge is that we satisfy that divergence A equal to 0, and let's set potential equal to 0. Also, gauge transformation so that vector potential plus gradient chi, where the phi prime is that phi minus 1/c partial chi partial T, that is under invariant. We call it is a gauge invariance. So in the Lagrange equation in the field, and partial T, and Lagrangian here, Lagrangian A vector dot, anyway, A vector dot. Here, classical mechanics, Lagrangian as the velocity, Lagrangian is the function of velocity and coordinate, but here coordinate correspond to the vector potential. So, and it is velocity correspond to the time derivative of vector potential. and the minus partial L partial A equal to 0. That is the Lagrange equation. From the calculation of this Lagrangian, we already define that this Lagrangian. I do not derive in more detail for the Lagrangian calculation. I will skip the classical calculation of this one, but here that is the result of this Lagrangian equation coming from that 1 over 4 pi integration, volume integration with 1 over c square partial square a partial t square plus Laplacian a equal to 0. That is, from this I do not derive in more detail, but anyway, then when we calculate this from the velocity a dot calculation, and here this makes that this one. So it means that this one should be 0. So Laplacian a plus 1 over c square partial square a and the partial t square equal to 0. That is the correspond to the Maxwell equation. Maxwell equation on the in terms of magnetic vector potential. So in the from this Lagrangian, I will deal with the Hamiltonian. So that conjugate momentum. Conjugate momentum is the pi. Let's define that the pi is that Lagrangian derivative with the time a dot. Then it is from the Lagrangian in the above a dot. Then it is 1 over 4 pi c and volume integration and 1 over c, 4 pi c, and also partial a, partial t plus gradient phi. That is, it is a conjugate momentum. One over c, because in the 2 and derivative with this one, and it makes that the 2 becomes a 4 pi, and also 4 pi and the real this one, and also derivative with this one also, it makes that the 1 over c here. So the Hamiltonian is that is a function of momentum, conjugate momentum, and a. Here I already said that the coordinate correspond to the vector potential. So from the classical mechanics and the volume integration is that momentum dot velocity minus Lagrangian is the definition of the Hamiltonian. So from this definition, and the Hamiltonian can be write down as that 1 over 4 pi c and volume integration and 1 1 over c partial a partial t plus greater than phi dot partial a partial t. That is the first term. And the real Lagrangian is that 1 over 8 pi and the volume integration, and also 1 over c partial a partial t plus greater than phi square minus col a square. That is that from the simple calculation, I will omit this detailed calculation. And anyway, the result is that 1 over 8 pi and volume integration, and also 1 over c partial a partial t square minus greater than phi square plus col a square. That is the result of this calculation. Here, so it is Hamiltonian, and let's then that is also correspond to the 1 over 8 pi volume integration with the electric field square plus magnetic field square. That is the energy. Then from this, that is corresponds to this. It is electric field and magnetic field. Then it makes that this vector potential representation. That is the first quantization of the Hamiltonian. And also, and here we will deal with the second quantization. Second quantization is the field quantization, and field quantization basic principle of the quantization is the commutation relation. And here commutation relation with the x and p, it is IH bar delta ij. That is the classical in quantum mechanical commutation relation. That is basic idea from the quantum mechanics. Here it is a commutation relation in this field is that the AI and the coordinate correspond to the magnetic vector potential and the conjugate momentum, and the R prime. Then it is IH bar correct delta ij and the delta function R minus R prime. That is that it is important relation to the field quantization. Here, and let's define that define field operator. Field operator or the field quantization, and the magnetic vector potential, it is RT. Then summation with momentum and wavelengths, and A it is a creation operator and the annihilation operator. That is already introduced from the harmonic oscillator, and the exponential I k dot r minus omega t plus and complex conjugate k lambda dagger exponential minus I k dot r minus omega t. That is here we define that it is a field operator. Then from the another, here we define that k lambda, and the polarization here we say that, and from the normalization factor is the 2 pi h bar c square over omega, and a k lambda epsilon means that k lambda it is a polarization factor, and the exponential I k dot r 마이너스 오메가 t 플러스 a k 람다 되고 epsilon star also k 람다 exponential minus I k dot r minus omega t. That is another, that is definition of field operator. And the Hamiltonian, from the above Hamiltonian, and also let's make that also gradient phi equal to 0, and let's only consider for the magnetic field, and in the it is a static field. Without the static field case, and let's ignore this term, and also in this case, and here Hamiltonian, let's calculate the Hamiltonian. So we should calculate this one, and let's calculate. And here call A square is that Laplacian A square minus divergence A square. So integration with volume integration, we call A square is that here in the this term equal to 0. So here in the gradient A is that from this definition, it is that here spatial derivative makes that the ik and the minus ik coming from here. So and it is square, means that the square is that the multiplication of the complex conjugate. So it is minus k square a square. So k means that omega over c square a square. So a already quantized. So and this term coming from that summation k lambda, and square means that 2 pi h bar c square over omega, and omega over c square, and a square, it means that a square means that a k lambda a 대거 k lambda plus a 대거 k lambda a k lambda. That is that this one. Also here we should calculate this term in the partial derivative with t 1 over c a partial t square is that 1 over c square, and partial a partial t makes that minus I omega, where the I omega is coming here. So it is minus omega square over c square a square. So it is that summation k lambda 2 pi h bar c square over omega, then omega over c square a k lambda 되고 a k lambda plus a k lambda 되고. So from this we should it is two terms. The interacting Hamiltonian is that 1/2 summation k lambda, it is h of omega, 1 over 8 pi. So 2 pi times 2, so it is over the 8 pi, so it is 1/2, and so h bar omega, and omega cancel with anyway, this term makes that omega, h bar omega. So ak lambda 되고 ak lambda plus ak lambda 되고, that is, we already know that it is the solution of the harmonic oscillator. So summation k lambda and h bar omega, and it is number operator k lambda plus 1/2, that is the number operator. It is a number operator k lambda is that ak lambda 되고 ak lambda. So it is that the solution is that harmonic oscillator, second quantization of the operator Hamiltonian is that harmonic, just harmonic oscillator. And also it has commutation relation of this creation operator or the annihilation operator is that equal to 1 from the quantum mechanical definition. So it is Hamiltonian. Also the result is that the harmonic oscillator means that electromagnetic wave is that harmonic oscillation of the magnetic field especially.